Meeting is okay, fine. Uh,
All good, sir. We can go ahead.
Blesson, can you give me a co-host? Yeah. So, good evening, all. So today our guest was Dr. Vinod Thomas. So I want to invite Dr. Ajit Gobi, our chair of IEEE PS Kerala chapter, to welcome all. So Ajit sir, you there?
Hello. Hello. Hello, Rahul.
Yes, sir. Yeah,
Hi.
I'm here.
Welcome, Dr. Vinod Thomas. Thanks for accepting our invite, actually. This is part of our international lecture series. Actually, it's actually a series started by IEEE PS chapter, 2021 Outstanding Chapter Award winner. So we have been taking different sessions, very vibrant session indeed for the last several months, and it has got wide interest in the international arena, and we are getting a lot of participants from the Kerala chapter, from India, and also from the global level. So I take this.
So your video is out now. Hello, sir. Yeah, okay. We can go ahead with Dr. Vinod Thomas. Actually, I will give a brief profile of Dr. Vinod Thomas. He is an assistant professor at École Centrale de Nantes, France. He has completed in BTech in Electrical Electronics Engineering from the University of Calicut, and MTech in Energy Systems and Engineering in IIT Bombay, and PhD in NIT Calicut itself. And he has served as a manager for solar PV projects in Reliance Industries Limited and Mahindra EPC Services Private Limited, Bombay, India. Has worked as an assistant professor at Rajagiri School of Engineering and Technology and Cochin and CUSAT. And he has also worked as postdoctoral researcher at École Centrale de Nantes, and he is currently working as associate professor there also. Yeah, Ajay sir, you there?
Hello.
Yeah.
Can you
please,
hear
sir.
me?
Yeah, yes. Now it's fine.
Okay. I think I was muted, right?
Yeah.
Hello.
Yes, sir. Yes,
Can you hear me?
all. Yeah, yes.
Okay. So I think my previous speech was muted. Can you hear me now?
Yes.
Yeah. So, so welcome, Dr. Vinod Thomas, for this international series. It's actually, we are very glad that our international lecture series is going well. And every month we have a webinar on or expert lecture on the subject of interest and in the upcoming field. So this title, the grid forming inverters and its role in future electric grids, is very important. As a person working in the renewable energy field, and especially on the distributed energy resources, I know the importance of grid forming inverters. We have a few installations of grid forming inverters in the very recent months because of special needs as because of the PV microgrid necessity there. So there are probabilities of getting grid, but we preferred for grid forming inverters in special areas where especially critical loads are needed. So it's a very interesting field, and experts, academicians, and researchers are looking forward to hearing it. On behalf of IEEE PS chapter, I welcome again Dr. Vinod Thomas for accepting our invite. I also congratulate Dr. Rahul Satish for organizing this webinar on behalf of IEEE chapter. Thank you so much.
Thank you, sir, and a warm welcome to once again. Yeah, Professor, please go ahead. Yeah,
Okay.
thank you.
Okay.
Yeah.
Hello, everyone. Thanks to Dr. Rahul for inviting me to this session, and thanks also to Dr. Ajit Gobi. It's my pleasure to be part of this international lecture series organized by IEEE's Kerala chapter, India, because I come from Kerala in India. So it's my privilege to be part of this lecture series. So I can see there are more than 80 participants, and I assume there will be participants from different profiles or even in power system from different levels. So it's not easy to make a presentation suitable to all the levels. So therefore I have made the presentation simple enough so that people with very little background on these topics can understand. And what I have done is at the end of the presentation, I will mention the reference, some of the references where you can find more information, because to put all the information within 1 hour talk is not possible. So it's always good those who are want to further do some work on this topic. It's necessary for them to go into details and identify some problems and work on that topics. Okay, so I go ahead with my presentation. So it's about the grid forming inverters and its role, how what will be the role of this group of inverters, which we call as grid forming inverters in the future electrical grids. So before starting, just a brief introduction about where I am and what I do. So I work, as Dr. Rahul mentioned, I am an associate professor at École Centrale de Nantes, Nantes University. It's located in France, the west side of France. And as in France, being a teacher, I am also associated as a researcher in a laboratory which is known as Nantes Digital Science Laboratory, LS2N. LS2N is in French. The abbreviation is abbreviation in French. And I work in a team which is known as Dynamics of Smart Grid team in this laboratory. So here we have some teachers and researchers, PhD students and master students who work on the broad theme of smart grid and the dynamics associated with the smart grid. And in this team, we are presently working on a few funded projects. One is a funded project with RTE. RTE is the transmission company in France, national transmission company. So they have given some funding to conduct some research on some topics which are interesting for them. So we have a few people working on that. And we have another project which is known as H2020 Positive project. So this is a 3-year project funded by European Union with partners from multiple countries. So each of the partners, they work on different topics. The broad area of research is to effectively integrate renewable energy into the grid. So that is the broad area of research. The more details can be found in the website. And also at my university, we at École Centrale de Nantes, we have a master's program on dynamics of renewable based power system. It's abbreviated as a DREAM program, Master in DREAM. So it's an Erasmus Mundus joint master degree. That is, it is a program which has got funding from European Union, and every year we select around 20 students from all over the world, and there is a full scholarship for the students to study this master program. So those students who get the scholarship, they don't need to pay fees, and in addition to that, they get around 1,400 euros per month as a scholarship. So it's an attractive program which started last year, and first batch of students have started their course, and the next year admission process is over. So every year, those who are, if you know any people who are interested to pursue this opportunity, you can check the website. Every year around after October, the admission process is starting for the next year, September batch. So, so with this introductions, I'll go to the topic. So why the topic of grid forming inverter is relevant these days? That is mainly because of the evolution of our power system, our electrical power system, or what we call as the interconnected grid, with a lot of generators of different types, thermal power plants, hydropower plants, nuclear, and nowadays with solar, wind, and many other renewable energy sources. These grids are constantly evolving in its nature. And as you can see in the figure, the conventional power system network consisted more of generators which are based on synchronous generators. And now, because of the focus all over the world to utilize more and more renewable energy sources, we are forced to use power electronic converters or inverters to interface these renewable energy sources into the grid. So we have nowadays, compared to a few decades before, we have more contribution of power from injected into the grid from the renewable sources such as wind farms or solar PV or some other sources of power. So each country, there are some countries which have high amount of installations of wind, and there are some countries which have a high potential of solar, and they try to exploit solar PV. But in either of these cases, we have more and more renewable energy, and we have more power electronic converters into the grid. So, it's a good thing that we move from the conventional power generation, fossil fuel based power generation, to renewable based power generation. But when the penetration or the percentage share of renewable energy is more in the grid, it causes some problems which needs to be addressed. So if we go ahead, without addressing these problems, if we try to achieve high renewable penetration without solving this problem, it will not be good for our electrical grid. It can cause sometimes grid outages. Everyone would like to have access to electricity 24/7 throughout the year. So we never want to operate in a condition where we have more renewable energy and but more grid outages also. So it's not a desirable thing. So generally, or what we say conventionally, when we integrate renewable energy into the grid, always we try to extract the maximum power available from the renewable energy sources, such as wind or solar PV, because we don't need to pay any money to, or it's free, these renewable energy sources, other than the installation cost after it is installed. When we have wind available, when we have solar radiation available, it is always advisable to extract the maximum power possible from these renewable sources and inject to the grid. So when we have a higher renewable power generation, what we do is we try to reduce the power generation from the fossil fuels and save money, save your cost there, and we inject, utilize the renewable energy to the maximum. But every country these days, they are trying to exploit the renewable energy potential to the maximum. So the percentage contribution of renewable can reach high levels. When the renewable energy started, the percentage contribution was always in single digit, 1% or less than 10%. But nowadays we can see that there are many countries where there are renewable energy sources. The contribution is higher, sometimes more than 30% or 40, 50, or even more than that. So let's take the case of Ireland. Ireland is a country in Europe which depends hugely on wind power. So the total Ireland is a small country compared to a country like India or France, but it has 4 gigawatt of wind capacity, and with this wind capacity, it can meet around 65% of its demand at some point. So, this 65% is a huge figure. It's a large figure in terms of renewables. So when they have more wind energy, they reduce their dependence on the fossil fuel based or the conventional power generation, and they try to extract the maximum from the wind energy. So this is the case of just one country, and there are a few other countries also who are actively pushing towards to have more or a very good share of renewable energy into their grid. So with these developments, we can always assume that maybe in the near future there could be a situation where 100% of the power demand at a point may be delivered by renewable energy sources. Maybe at some point, may not be throughout the day or throughout the year, but at some point in a day, at some point it can happen like that. When the wind is good and when the solar PV is very good, it will have high penetration, almost 100%. So it is essential for power system researchers or the companies who are involved in the power generation, distribution, and distribution transmission. They need to be prepared to face this situation and to face the challenges associated with this situation. So conventionally, our electrical grids, they are designed to operate with synchronous generators, because we started like that, with synchronous generators, with steam turbines, turbine driven synchronous generator. So these synchronous generators, they have some inherent capability to ensure the stable operation of the grid during any kind of contingencies, such as fault or maybe some heavy load turned on or turned off, or maybe one generator stopped the generation. So synchronous generators, they have the inherent capabilities, because a synchronous generator, it is a rotating machine with a huge mass which is rotating at a high speed. So when some load is turned on, because of the inertia or the rotation of the physical machine, it can ride through these kind of contingencies without much difficulty. But when we have a reduced presence or maybe no presence of a synchronous generator in the grid, electrical grid, there could be problems associated with that. There was a survey conducted as part of one European Union project. A survey was conducted among the transmission system operator companies in Europe. Each country in everywhere in the world, they have each country have their own transmission system operators, so TSOs. So a survey was conducted and they were asked to rank what are the challenges they feel which is associated with the higher penetration of renewable energy into the grid. So they had listed more than 10 challenges. So I just listed here the top 5 of these challenges. So among these, the first ranking is given to the challenge decrease of inertia in the grid. And second one, there are resonances due to cables and power electronic converters, because power electronic converters are static devices and they operate at very high they operate at a higher smaller time constant, so there are resonances and other phenomena. And the third challenge they have mentioned is the reduction of the transient stability margins. And some 4 and 5. So I have just highlighted the first one and third one because that is these are the 2 challenges which may be addressed with the help of grid forming inverters. So other challenges we may need other solutions for that. So the decrease of inertia and the reduction in the stability margin. So these are the 2 challenges. So we'll go a little bit in depth on this, on the reduction of inertia. So if we can represent visually the electrical grid, we can represent with the help of a simple figure, this drawing. When we have multiple generators, they are coupled to a common grid, and all these generators, they operate in a synchronism. They operate at the same speed, delivering power to the grid, and they give rise to some frequency which is associated to the speed of rotation and the number of poles of the synchronous generator. So when we have synchronous generators driving the power system, and these are the main power generation, and they have a rotating mass associated with the synchronous generator. And the grid frequency, as I mentioned, the grid frequency, whether it is 50 hertz or 60 hertz in different countries, they have different values. It is determined by the speed of rotation of the synchronous generator. And this frequency grid frequency is something which needs to be stable, like the voltage. If a country they have the RMS voltage, nominal voltage of 230 volt, it is necessary for the grid operator to ensure that these values are maintained, or at least it should be maintained in the acceptable limits. So the grid frequency will remain stable or almost constant when there is a power balance between the mechanical input of the synchronous generator and the electrical output or the electrical load. So if there is power balance between the power generation and power consumption, the grid frequency will remain stable. And if some kind of power surplus happens, power surplus can happen due to one load turning off suddenly. It can happen at any time in a grid, or maybe one additional generator is turned on. So these kind of contingencies or perturbation can cause a power surplus in the grid, and it can cause a momentary increase in the frequency. And this frequency, naturally, there will be some controllers in the power system which will sense the increase in frequency, and then it will try to stabilize or bring back the frequency to the nominal value. And also the opposite condition can happen when there is a power deficit, and there is a power deficit, it can cause a momentary drop in the frequency. So coming to one equation, so the frequency, it's determined, it's written generally by the symbol F when it is in the hertz, and when it is in terms of radians per second, we use the symbol omega. So the rate of change of frequency, the d omega by dt in a synchronous generator based power grid, electrical power grid, can be given by this equation, which is a standard equation, which is equal to omega star, which is the nominal frequency, divided by 2h eq multiplied by pg minus pl. So here pg is the power generation and pl is the power of the load. So from this equation, we can understand that when PG is equal to, when the power generated is equal to, when the load is exactly matching the power generated, that will give to, the right side will become 0. That means there will not be any change in the frequency. That is d omega by dt will remain as 0. It will remain constant. So that is the condition when the power is balanced, then the generation and load is balanced. And in this equation, we have a term which is H. It is actually an inertia constant. Inertia constant, which is given in seconds, or megawatt second divided by MVA. So this inertia constant for one synchronous generator, this inertia constant is easy to understand. It is the energy stored, inertia constant. If you consider the other unit, megawatt second by MVA, it is the energy stored in the rotating machine divided by the power rating of the machine. So it is an indication of the kinetic energy stored in the machine, and we scale it to the power rating of the machine. So larger machines, so we can have inertia constant, the range of values are almost same. So when we divide it divided by the power rating of the machine, so whether it's a large machine or small machine, the inertia constant will be almost in the same range. So when we consider a power system with just one machine, we have just one inertia constant of that machine. But when we have power system, when we consider power system with a multiple generator, there will be multiple inertia constants. Say, let's consider the second equation. When we consider a system with an n generator. So when we have n generator, we need to consider the equivalent inertia constant of the overall electrical grid. To find that, we need to take the inertia constant of each machine, multiply by the power rating of each machine. So that is HI multiplied by SI. Then add it with the inertia constant of the second machine, then multiply with the power rating of the second machine, and so on. For the n machine, we can do that, and divide it by the total power rating. So SB will be the base power or the total power capacity, which is SI plus S1 plus S2 plus S3, and so on. So when we have multiple generator, there will be something known as the equivalent inertia constant for the overall system. So this we can write. Sometimes people refer it as a total system inertia for a grid. So one thing from the first equation here, we can see that when we have lower values of inertia, for the same case, when there is a PG and when there is power generation and load consumption, when we have lower values of inertia, the right side, the denominator is smaller, that can cause higher values for the d omega by dt. That means with lower inertia constants or with lower inertia of the grid, it will lead to higher rate of change of frequencies. So in the figure on the right side, for one event such as a generator tripping, or when a generator is turned off, what happens when the power system or the grid have a high inertia and low inertia. So that is shown. A typical curve is shown here. So at some instant, the one generator is stopped, and we can see that there is a reduction in the frequency, and there is a tangent drawn at that point, and which is marked as a Rocoff rate of change of frequency. Rocoff is rate of change of frequency, which is d omega by dt, the rate at which the frequency is dropping. So it is an indication. Rocoff is an indication of whether the system is becoming unstable, whether it is going to an unstable region. So instead of waiting for the frequency to drop to some value, or instead of waiting for the frequency to reach above some value, by analyzing the values of rate of change of frequency, we can see whether the system is going to become unstable or not. So with a high amount of inertia, we can see that the rate of change of frequency magnitude, it is less, and the frequency drops to some low value, and after some time the controller, frequency control will come into picture, and it will try to bring the frequency back to the nominal or the initial frequency. But by the time the frequency drops and it reaches the lowest point, which is known as the frequency nadir, the lowest point of frequency after a disturbance. So after that, the frequency comes back. So with lower inertia of the grid, we can see, because of the lower value of HEQ, equivalent inertia constant, the frequency, the lowest frequency will be the magnitude of deviation, the maximum magnitude of frequency deviation is higher. So when we have grids with very low values of inertia, so the equivalent inertia will be decided by the inertia constant of each machine. So when we have 10 machines, and out of which 8 machines does not have an inertia, so inertia will not be present when we have inverters. For rotating machines, there will be some amount of inertia. So when we have higher renewable energy sources, and when we have low inertia, that means after some kind of a disturbance, the frequency can drop to a very low value below the under frequency tripping point. So there will be some under frequency relays in the power system which will trip when the frequency goes below that value. So with lower inertia, so there could be more chances of the power system getting turned off, or we get grid outages due to the frequency going below the acceptable range. So it can happen with a low inertia. So that is about the inertia concept and the rate of change of frequency. The overall grid inertia is one term which we always use to show how the system can handle this kind of disturbance. So when we have a system, a grid with high inertia, that system will have less frequency deviations, and it will be more stable in terms of frequency point of view. And the other challenge which is mentioned by the transmission system operator is the reduction of the transient stability margin, or the rotor angle stability. So for those who don't remember, the rotor angle stability is the ability of the synchronous generators. When we have multiple generators, how they are able to maintain its synchronism in normal or abnormal condition. So that is meant by rotor angle stability. So after any kind of disturbance, there will be some acceleration or deceleration of the synchronous generator, and instability can happen when the system cannot absorb the kinetic energy released by the synchronous generator, when some kind of perturbance happens, or even vice versa, when there could be some kinetic energy stored in the synchronous generator after a disturbance, depending on the nature of disturbance. So when we have higher renewable energy generator, each synchronous generator, it releases or absorbs. It needs to absorb more energy from the system after a disturbance. The disturbance will be the same kind of disturbance can happen in the system. But when we have more renewable generators and less synchronous generator, there are more chances that the synchronous generator, which are a few in number, they are handling all this renewable energy. They are handling the storage and release of the kinetic energy. So there are more chances that the synchronous generator will lose its synchronism and it will become unstable. So conventionally, so these are the two problems. So coming to our, before coming to the grid forming concept. So conventionally, when we want to integrate renewable energy such as solar PV or even battery, or if you want to integrate to the grid, generally we use what is known as grid following inverter. So most of the conventional or the traditional inverters based on which work on solar PV, such as grid connected grid tie inverters without any battery storage, these are all grid following inverters. So it could be some three-phase inverter with some IGBTs or MOSFETs, depending on the power rating. They inject power to the grid. They extract maximum power from the, there will be some converters to extract maximum power from the renewable sources, and then they inject the power to the grid. So these are working as grid following inverters. So a simplified diagram of the grid following inverter is shown how the block diagram will look like. So these are called as grid following inverters because they follow the grid voltage and frequency. They follow the grid voltage. So it just senses the grid voltage and the frequency and the phase angle of the grid, and it injects the power to the grid at the point of common coupling, which is short form, which is PCC. So they inject, generally it injects maximum power, but there are new technologies which can inject even power less than the maximum power. But the basic idea is they follow the grid voltage and frequency. They don't try to, it's like grid following inverters are like slave. They just follow their master, which is the grid. They don't try to interfere with the grid voltage magnitude or the frequency of the grid. So one feature which was requested by the electrical distribution companies, transmission companies, when we had renewable energy sources connected to using inverters, was that they initially wanted the inverters to have disconnect themselves from the grid when there is when the grid voltage is not in the acceptable limit, when the grid frequency is beyond the limit. They wanted the inverter to be disconnected, or it should be shut down by itself. In that case, when there is no grid, it should not work. So that was the requirement from the grid operators in the earlier days. So this feature is generally known as anti-islanding feature. So anti-islanding feature, when these solar PV inverters which does not have any battery storage. So if we use this solar PV inverters during the daytime, even if you have sunshine and if there is no grid, maybe due to some reason, due to some cyclone or something, there is no grid available. So even though we have solar PV available, even though we have wind available, because of this feature, because of the grid following nature, they are not able to inject power to the grid. So that is.
I know you're small. No, just
Okay. So mic is on. Okay.
Yeah.
So this requires this feature, grid following inverters. They require the accurate estimation of the phase angle of the voltage at the point of common coupling for its proper functioning, because it is following the grid voltage So it needs to know what is the grid voltage, what is the instantaneous value of the grid voltage, what is the phase angle, frequency, everything it should sense. So for that, there is a dedicated synchronization unit in the grid following inverters. Generally, it is known as a phase lock loop, PLL. So it grid following inverter function based on with the help of a phase lock loop. So the basic functioning of a grid following inverter. We can represent a grid following inverter like a current source connected in parallel with a high impedance, injecting power to the grid. On the right side, we have a simplified representation, and on the left side, we have the phasor diagram. So normal condition, we have phasor diagram given by the Kirchhoff's voltage law. We construct the phasor diagram with that. The converter voltage VC is the sum of vector sum of the voltage drop across the grid impedance and the grid voltage. And when the grid voltage is disturbed, when the grid voltage is disturbed, the VG changes, the grid voltage changes. So when grid voltage changes, and grid following inverters, they generally give the same amount of, they are acting like a current source, so they won't change its current in this case. So when we have the same current and the grid voltage is different, if it is different, the voltage drop across the grid impedance ZG will be different. So naturally, the voltage VC will be the new voltage across the converter will be VC dash or VC prime. So it will be a new value when the grid voltage is disturbed. But we can see that there is no change in the magnitude or the angle of the grid current. IG prime will be the same as the IG when the grid voltage is disturbed. So because it's a grid following inverter and it is delivering almost the same current, when the grid voltage is disturbed also it will deliver the same amount of current. So when it does that, the converter voltage will change by itself without changing the current injected. So this is grid following inverter, and it acts like a current source feeding power parallel to the grid, and it cannot control the voltage and frequency of the grid, and it cannot even control its own voltages. The grid following inverter, as you can see in the previous, the new when the grid voltage is perturbed, the converter voltage is also changing. So it is not able to control anything. It just feed power parallel to the grid. And we need this phase lock loop to synchronize the output voltage of the inverter with the grid voltage. So coming to the grid forming inverter. So how it is different. So the grid forming inverter. So physically, grid following and grid forming inverter will be the same. Physically, in terms of the converter topology, it is the same. We can use the same inverter as a grid forming and grid following by changing the control algorithm. So in terms of hardware, nothing changes. What we need to do is in the controller, we need to make some changes to change its behavior. So the origin of the necessity of grid forming inverter started with the concept of microgrids, because in microgrids we wanted to use a lot of renewable energy sources in standalone mode without connecting to the grid. So in that mode, we need to have inverters which operate like a grid forming inverter. So grid forming inverter, so as the name indicates, they can form by themselves as a grid for other generators. So that means it can act like a master for other generators to follow. So we can have one grid forming inverter and other inverters in the grid following mode in the system. So this is considered as a promising solution if we want to have higher penetration of renewables to the grid without causing stability problems caused by the traditional grid following inverters. So how the grid forming inverter, the same case of the simplified representation of a grid forming inverter. It can be represented as a voltage source in parallel in series with an impedance. And in this case, we can see when the grid voltage is disturbed, when the grid voltage is disturbed, in grid forming inverter, the internal voltage will remain same. The E and the E prime will be the same in this case. So when the grid voltage changes, the grid current should change to if we want to ensure that the Kirchhoff's voltage law it is maintained. And as per the phasor diagram, we can see when this happens, in this case, when the grid voltage is changed from VG to a new value, the IG will should change, so that because the grid internal voltage is maintained constant. So that is the phasor diagram of grid forming inverter and the simplified representation of the behavior. So grid forming is considered as a voltage source in parallel with a small impedance. So it behaves as a voltage source behind a small impedance. And the currents in the grid forming inverters, it is determined by the network condition. And therefore, it can change rapidly depending on what is connected to the output of the grid forming inverter. But in grid following inverter, the currents injected will be almost constant, whatever happens to the grid. So it's a tabular comparison for an easy understanding of grid following. And so the main objective of grid forming inverter is to set up or control the AC voltage and the frequency. But the grid following inverter, the main control objective is to control or regulate the amount of power injected to the grid, and it will control mainly the current and the phase angle of the current injected. And grid following inverter. So the grid following inverter, it can operate very well with a stiff grid which where the frequency and voltage is almost constant. But grid forming inverters can work. It doesn't need a stiff grid. That means it can work with weak grids where the voltages and frequencies can change frequently. And a grid forming inverter does not need phase lock loop. So, so grid forming inverter, other than the basic concept, there are from the transmission system operator, they expect a lot of functionality. So grid forming inverter is some kind of inverter which provides some kind of services or additional functions to make the power grid stable. So they expect a lot of things from the grid forming inverters. In terms of behavior, that they expect that grid forming inverters, they improve the frequency response and provide better control. They provide the active power requirements to the grid, and during fault, it should provide some kind of support. It should be able to ride through the fault, and it should be able to provide the reactive power requirements and also things like a black start or idling operation. That means it should be able to. Black start operation means it should be able to start by itself from without any other generator. It should be able to start by itself from the zero position. So that these are some of the requirements from the grid forming inverters or expectations from the grid forming inverters. So based on this, there is some kind of classification because there could be many manufacturers, there could be many people who make inverters which they say as grid forming, but all these inverters may not have all the functionality. So there is a classification, class 1, class 2, class 3. Class 1 grid forming inverter is considered as the inverter which provides just the basic grid forming functionality, and class 3 will provide many high functionalities. So overall structure, how it looks like, the main change is in the control structure. In the inner loop, compared to grid following inverter, it is almost the same. In the outer loop of the grid forming inverter, there are some changes in the grid forming, how it depends, how it changed from, it is different from the grid following inverter. So there is a loop which is called as the power synchronization loop, which consists of two separate loops, frequency and angle loops. And there is another loop for the, in the outer loop for the voltage profile. So this is a general structure, and there are different algorithms proposed by different researchers. So it is grouped as a single one, but the exact strategy will be different. We will not go into the details of the different control strategies. So the overall objective of the outer loop, which is the power synchronization loop, which involves power synchronization loop, is to calculate the frequency and the voltage angle. And how this system, these two, frequency loop and angle loop, they are doing it, that will vary according to the control strategy. So I will briefly mention the two control strategies which are popular. First one is the power synchronization loop, which is implemented with a droop control. So here the objective, the basic objective is to calculate the omega and the theta. So that is calculated based on the standard droop control equation. So here from this equation, when we implement this control algorithm in this control loop, we can find out the omega and the theta information from the control loop, and we can give to the inner control loop. And the other the control algorithm which is reported in literature is the power synchronization control. So here we do the power synchronization by emulating the behavior of a synchronous machine. So these kind of synchronization algorithms, there is some different terms are used. There are different terms given for this different control algorithms. There are terms called virtual synchronous machine, virtual synchronous generator, synchroinverter. So basically, the basic idea is this inverter, grid forming inverter, will try to mimic or emulate the behavior of a synchronous machine in its controller. So with that, it provides the grid forming support for the grid. And because this grid forming inverter, it's a technology which has progressed immensely during the last decade. So to deploy these grid forming inverters in our power system, on a large scale, it's not good to implement on a large scale before testing it in complete with all the things. So there are a few pilot projects done at different parts of the world where they try implement, they use a grid forming inverter, they connect it to a grid, and they do different kind of testings of this inverter in actual grid condition. So when it is tested with actual grid condition, we get a very good or accurate results of the true behavior. If it is just a laboratory testing under ideal conditions, the actual behavior may not be the same because the grid behavior is not predictable. There are a lot of dynamics involved in that. So there are a few pilot projects implemented in the last decade. So one pilot project is in Zurich, where they implemented grid forming inverter of 1.5 megawatt and with some energy storage. So all this, when we mention about inertia, when we want to improve the grid inertia, it is essential that if we use grid inverters for that, there should be some kind of storage involved in that. Otherwise, we cannot, without storage, we cannot provide the inertia. We cannot increase the inertia. So in this project, they have implemented grid forming inverter with some batteries, And there is another project in USA where they implemented a voltage source converter of 200 megawatt capacity. So these are HVDC converters which are connected in a back-to-back configuration. But interestingly, there is no HVDC transmission line. The objective is to provide the grid forming control in this converter to improve the stability of the grid. So it's HVDC converter, but without any transmission lines. And there are a few projects in Europe also where they are testing this grid forming inverter control topologies with the actual grid. So they are implemented in small scale in at different places. And there are even commercial products. There are companies, for example, this HVDC project in USA, it was implemented by ABB, and the ABB they have some products which have this kind of grid forming features for different applications. So this is a technology which is now getting commercialized, but it's not yet fully or used in a large scale these days. And okay, so I'll wind up quickly. So some of the challenges of a grid forming inverter. So every new technology, when it is coming up, it will solve some problems, but it will again cause some kind of problems, some other problems. So always researchers will try to solve the new problems. So one such problem is when we use grid forming inverter in weak grids, it is good, but when we use it in strong or stiff grids, sometimes loss of synchronism can happen with the grid, and there can be some kind of power oscillations. So when we use grid forming inverters, we need to understand this problem in detail. It's mentioned in brief only here, but there are issues related to the synchronism of the inverters to the grid, even the grid forming inverter. So there are a lot of research going on this topic, but still there is further research needed on this topic. And also the grid following inverter, they have the benefit that in terms of in the case of any fault, there will not be very high currents flowing through that. But in grid forming converter, the currents are not controlled, only the voltage is controlled. So during any fault, it can cause high currents and it can damage the hardware, inverter hardware. So how to overcome this issue without losing the functionalities of the grid forming inverter? So that is one challenge. And there are a few research problems I listed out. Okay, there are, as I mentioned earlier, in grid forming inverter itself, there are different control algorithms or schemes. So which is the best? So that is one question people have tried to analyze. Or is there a best control scheme? Because we don't know, maybe depending on the grid condition, the control, we may need to use different control scheme. So we are not sure that the same control, one control scheme will be the best for all conditions. And in a grid with a lot of inverters, what will be the best, what is the best number or the optimal number of grid forming inverters needed, and what should be the power ratings, and if we want to position, if we have the freedom to choose the location of the grid forming inverter, how should we position it? So optimal allocation or optimal location of the grid forming inverter in the grid to ensure the stability is improved to the maximum. And when we have grid forming inverters of multiple algorithms, multiple control scheme, or with different manufacturers, how to coordinate, whether there will be additional problems because of this different control algorithms. So that also, it's one interesting topic to be explored. and what could be the future. So there is no doubt that the grid forming inverters are going to be implemented on large scale in the future power system. Maybe sometimes the name of the grid forming inverter may be different depending on the manufacturers. They can provide the different names sometimes, like smart inverters or something like that. So, but the basic concept is to provide a support to the grid instead of destabilizing the grid. Provide a support to the grid to improve the inertia of the grid, to improve the the transient stability of the grid using the inverter. So if these inverters can provide this thing, it will be a good contribution to the future electrical power system. But still, this grid forming inverters, there are some lack of standards or definitions. So if there are no uniformity in the definition of or the functionality of the grid forming inverters, it could be confusing. The terms could be confusing. So there is a need for a unique or clear definition of this grid forming inverter and its functionality. So, so there is some work going on this area so that is up to the TSOs to make some definitions or expectations of the grid forming inverter, and also how to test when we have grid forming inverters with different levels of functionalities. Like as I mentioned, class 1 will have be the basic grid forming functionality, but there could be a high-end grid forming inverters. So we need to develop some suitable processes and test cases for testing and validating the grid forming inverter. So these are things which will help to have a higher share of grid forming inverter in the future power system. So, so that is my viewpoint on this topic, and the topics covered on this presentation is we can go into the details. There are a few good research papers which cover most of the details of the control schemes, and these are some papers which give a general picture. And if you want to go in details of a particular scheme and something, you need to go into the references of this paper. And one more resource I would like to share with you is I can share in the chat box. I will share one link. Okay, so this is one website where those who want to do something to get some hands-on experience on working with the grid forming and grid feeding similar inverter models, there is a free repository available with grid forming as well as grid feeding models. So you can these are MATLAB simulating models freely downloadable from this website. So this was developed as a part of a European project, and they have made some repository for public all researchers and teachers or students to experiment on some of these technologies of grid forming, to do some comparison and other things. So it's free for all. Just as they mentioned, it's when you use these models, it's good to refer or cite their references. The group of people who have worked to make this, so it's good to give them credit on that. So it will be an interesting thing to those who want to get some hands-on experience on this. So with this, I would like to wind up.
Yeah, thank you, Dr. Vinod. And we can go ahead with the questions, right?
Okay.
Yeah, I will assist you in that. There are so many questions in the chat box.
Okay.
I will read by once.
Okay, I'll try to answer what possible.
Yeah. Actually, Sebastian is asking Slide number 8, does the plot assume no fast action devices such as power electronic devices installed on the grid? Because if there are some such devices installed, they should be capable of reducing rock off and lowering the deviations of frequency. In slide number 8.
Okay, okay. So this is a standard waveform where a system with no, not fast-acting devices. Is the question clear? So
It's
this
actually
is
asking if does the plot assume no fast action devices installed on the grid? Does the plot assume?
yeah, it
I
is.
think
It's based on that assumption. Yes. Yeah. It's based on that assumption that no power electronic devices are installed.
Right. So this is Sebastian. So thank you for answering my question.
Okay.
So I was just curious about the plot because, say, if we have these power electronic devices and energy storage that supports the renewables, then this can be potentially offer solution to this low inertia problem, right?
Yes, yes, yes.
Okay.
So even the when we have the graph which shows the low inertia is a system where we have a lot of inverters and which does not provide any kind of support, frequency
Okay.
support for that. So in that case, we don't have the frequency deviation will be high. So the plot is just a typical curve to show the difference between a grid with how the frequency graph will vary when the system will have high inertia and low inertia. So each case, it's not it does not assume that it will have some kind of fast acting power electronic device. No.
Okay, got it. Thank you.
okay, thank you. Thank you, Sebastian. I will move up to next one. And Praveen is asking, what is the scope of GFM in large grids like India? It's a common question, and how combined question is also there. How grid forming inverters is important for Indian power systems?
Grid forming, it's not the scope of grid forming inverter is not based on the large grids. It depends on the type of grid. If the grid is large and if there is not much, if there are not much renewable penetration, if the penetration of renewable is very less, or maybe 1%, 2%, or 5%, it doesn't have much scope for from the transmission system operator point of view. They won't be interested, and even these days, many countries, especially European countries, are exploring this grid forming inverter. They are interested in this only because they have more renewable, and they have conditions where the percentage of renewable is more. So if it is not much, it won't be not interesting now, maybe later. So in India, I think still the penetration of renewable is not in that level, but I think it will be better to do some, as Dr. Ajit Kobi mentioned, there are already some kind of pilot projects. People are experimenting with this. So it is necessary to try and deploy these technologies so that when it is time, we are ready to deploy it on a large scale.
Okay. And one more thing is Gajendra Singh asking, please share your thoughts on high frequency GFMs for future grids in megahertz.
Okay, sorry, I'm not able to answer that. I don't, or maybe I don't understand the question. High frequency. So I don't know. Is it mentioning about the switching frequency of the? So this grid forming inverter, it does not. We don't differentiate between the grid. We are not much interested in the switching frequencies of the, or the maybe even the topology of the grid forming inverter. So the main focus is on the control, how it supports the grid frequency, which is in hertz. So if the frequencies are in megahertz, also, if as long as it is not interfering or causing any problems, it won't be an issue. Maybe. Okay. Okay. And hello. Hello. Rahul.
Hello. Hello, Vinod.
Yeah. Okay, I'll just read through that. One question is why and how PLL is not needed. So the why it is not needed is grid forming. The principle of operation is different compared to the grid following inverter. It depends on the power synchronization equation. Based on that, it synchronizes itself with the grid. So the concept is a bit different. I cannot go into the details of that, but some of the references which I mentioned in the at the end of the slide, it can give more details. But to add to that, the basic grid forming inverter can work without a PLL, but there are configurations which use a PLL also to improve the performance. So that's how it works. And
the frequency is input variable for this. When you have grid forming one, the frequency itself is something which you are going to give into the as an input variable. It's not derived from the grid. That is what I think.
Yes. Yeah. So in the diagram showed the voltage and frequency. That is something which is decided by the grid forming control. So, but in grid following, it is trying to sense the grid frequency and try to work in parallel to that. Okay, can we synchronize? When can we synchronize stiff grid with the grid forming inverter? It is possible to synchronize stiff grid, but I read some paper where they did some work on that. It has some issues like grid forming inverter. When we connect to a stiff grid, it causes some kind of power oscillation. So they did there is one paper where they analyze this problem exclusively. So it is possible to synchronize with the stiff grid, but there could be some problems. But it is meant to operate mainly it is meant for weak grids, but it can work with a stiff grid also. How to determine the droop coefficient effectively?
And few of them are asking the controllers performance in this. May I read this?
Which is it's after about the controller. I can't see the question. But
the impact of different types of grid forming algorithms and controllers on performance.
There are like 4 or 5 grid forming control algorithms. So each has its own merits. Like one thing I can add to that is, as I mentioned, there are a control scheme which try to emulate or mimic the behavior of a synchronous generator. So there are some control scheme which try to emulate the full behavior of the synchronous generator. There are some control scheme which try to emulate a simplified model of a synchronous generator. So when you try to emulate the full behavior of a synchronous generator, it is good, but the system will become complex, and sometimes because all this controller, it is working in a controller in a system, so sometimes it can cause some kind of instability in the controller itself. So always it is generally industry, the trend is they prefer simple solutions. They don't want to work with very complicated controllers which can cause some problems or instabilities. Only if it is fully proven under all contingencies, it is good for them. But advanced fancy controllers which are too complex, which are proven to work only maybe only if it is tested only for some ideal conditions, it's not good. We need to test it in all conditions. So as I mentioned in the last slide, we don't know whether which control algorithm would be best, or maybe for different condition we need to change the control algorithm, type of control algorithm for the grid forming itself.
Rahul, can I ask a question in between?
Yes, ma'am. Yes, ma'am.
Good evening, sir. I'm Dr. Shobha Manekal. Is there any work that has been done with adaptive controllers for this? That is, it can adapt itself to the changing environment.
Yes, some work in the area of virtual synchronous machine, where we mimic the behavior of a synchronous generator in a grid. There in a physical synchronous machine, we cannot change the inertia because it is something which is inherent to the machine. But in an inverter, inertia is a term which we fix. But of course, inertia will not come without adequate storage. We should have adequate storage, but it is possible to have an adaptive kind of control scheme which can give a higher virtual inertia at some point, and maybe depending on the condition, it can change the inertia parameter also depending on the condition. So there are some work if you search on the adaptive inertia, there are a few, I think, few papers on that.
Okay, sir. Thank you. Thank you.
Okay.
Thank you, ma'am. Dr. Vinod, we can take one more question. And the
Okay.
last, is the anti-analytic feature present in GFM, and how can the TSO have a control over the GFM similar to that of conventional synchronous generators?
Okay. Anti-islanding feature in grid forming inverter, it's supposed to, it is given a functionality to work in islanded mode. But there are some control scheme when a manufacturer makes one product, they try to use it, they try to make it such that attractive for all kind of customers. So there are, I saw some inverters where they provide some kind of switching, that you use the same inverter as a grid forming inverter as well as a grid following inverter, and they switch to the other mode based on the condition. We can set it in which mode it should work. So if it is grid forming, it will not be anti-islanding. But if you are changing it, the mode of operation, into grid following, then yes, anti-islanding. And how can the TSO have a control over the grid forming inverter similar to that of So the control of TSO on the grid forming inverter, or not only grid forming, and for all the renewable, that is a challenge, because this TSO, it's difficult for TSO to control all the when most of the renewable sources are not they don't have very high power capacity. So it's difficult for the TSO to have a control over the individual individual inverters, even if it is grid forming or grid following. So there are concepts, emerging concepts such as virtual power plants. So in one of our project, we are working on that. In virtual power plant, what we do is the generators are grouped into a common power plant. So it behaves, the power plants which are located at different locations, they are grouped as a single entity to the TSO, transmission system operator. So the TSO will give a common command or control to the virtual power plant, and it is up to the virtual power plant operator to distribute or redistribute the power or the support among the different renewable different inverters in their virtual power plant. So for TSO, they can for small generators it is difficult for them. When it is grouped as a common big power plant, then it is possible, maybe with the concept of virtual power plant, maybe possible.
Thank you, Dr. Vinod. Thank you for all the participants.
Okay.
And
Okay.
yeah, we are heading the time. Yeah, so
Okay,
I think
so,
we are closing at 9:30. So
okay.
yeah, on behalf of IEEE PS Kerala chapter, I would like to thank you, sir,
Thank
for attending our session, and I would like to thank all the participants, those who are participating vigilantly, and for the smooth conduction of QA session also. And thank you for once again. Thank you, Ajit sir. Thank you, Shobha ma'am. And yes,
you, Dr.
thank you.
Vinod.
Thank you all.
Thank you. Thank you, Dr. Vinod from the chapter.
Bye.
Bye.
Bye bye. Thank you. Thank you. Bye bye.